Uh, the first problem, a 45 Newton horizontal force is applied to a 12 kilogram box initially at rest, sitting on the floor. Okay, so up here I've given to you some letters that we would typically use for some common forces. So lowercase f for friction, W for weight, and please note that weight is equal to an object's mass times 9.8. And T for tension, and F sub N for normal force, and F with subscripts for any other forces, okay? So we first start off by drawing some picture of our box, okay? And we are going to label all of our forces originating at the center of mass of the object. So that little dot there represents the center of mass of the box. And when I apply a force, like for example, the force of gravity exerts weight, some kids like to draw it like that, but we're going to specifically ask you to always originate your vectors with the tail of the vector at the center of mass, okay? So the weight is down, the floor is there to support the weight with the normal force, and remember the normal force is normal to the surface. So since the floor is horizontal, normal to that would be straight up, okay? And then a 45 Newton horizontal force, they didn't say if it was to the left or to the right. I'm just going to assume it was to the right. And so I'll label that F1. I could have said F1 equals 45 in my diagram if I wanted to. Okay, so there are the forces acting on the box. Next, two forces act on an object, and one is 50 newtons directed 24 degrees north of east, and the second is 32 newtons north of west. They don't mention any other forces, so we're going to assume that the only two forces we care about are the ones they mention. So once again, I put it on a coordinate system, and there is my center of mass of the object. So my first force, 50 newtons, right there. And of course, my angle 24 degrees north of east would be that angle right there. Okay? And then my second force, 32 newtons, 48 degrees north of west. So 48 degrees would be right there. Okay? And you can tell I'm not drawing it to scale very well. That's okay. As long as you label your diagrams with the angles and the magnitudes of the forces, you don't really have to pay that much attention to the scale of the vectors. If you want to try and get close, it helps you understand it a little better, but it's not really necessary. Okay? All right, we're on number 3 now. A crate with a weight of 250 newtons is pulled along a horizontal surface with a force of 12.5 newtons at an angle of 17 degrees to the horizontal. Here now we talk about there is some friction. So a coordinate system, I drew a coordinate system, and I will choose my x-axis to be the direction of motion or the direction it would move, okay? So later we're going to look at problems where there's boxes on an incline. So if that's the case, I would choose my incline to be the x-axis. And we'll show you that in just a few minutes when we do one of those problems. But now, right now it's a horizontal surface. So the weight, well, first of all, my center of mass of the crate is right there. And its weight is going to be straight down. Because it's a horizontal surface, the normal force will be straight up. And all right, so we have the weight and the normal force. Then our force that we are pulling or pushing on the box with, it tells us is 12.5 newtons, and the angle 17 degrees, of course, is going to be right there. And then the sliding friction, remember, not fiction, friction. There is, friction always opposes motion. So if I'm trying to pull it to the right, my frictional force will be to the left. Okay, there are the forces acting on the crate. All right, next one, a rope. Here's an example of where our surface is tilted. Okay, it's on an inclined plane, and the angle, which I've labeled here with theta, that's what's 25 degrees. Okay, so the rope is this blue line that I've drawn here holding the rock in place. The rock has weight, so that's always straight down. Even though the incline is a ramp, the weight is always straight down. The tension is always going to be in the direction of the string. Strings can only pull in the direction that you stretch them, okay? And then the normal force, you can see here the normal force for this one is not straight up because it's normal to the surface. So since the surface is tilted at an angle, the normal force is always tilted, but you'll notice that it is perpendicular to the surface, okay? That's why it's called the normal force. The word normal means perpendicular, okay? And also I've shown here, just so you know, because this problem says we have a 20 kilogram rock, kilogram is mass. Mass is not a force. So we have to convert mass to weight. Weight is a force, and weight is calculated by multiplying the mass by 9.8. So the value of this weight of the rock is 245 newtons. Okay? And not today, but later we're going to resolve any forces that are not on the x or y axis into their x and y components. And you can see here, this weight force is not on the x or the y axis. So I need to resolve it into its x and y components. And I want to show you that the angle of incline that the ramp is raised shows up right here where I've drawn it with the orange line. And I want to show you why that's the case. So if you look at this large right triangle, okay, that includes this dotted line, if this is a right triangle between the solid line and the dotted line right in here where I'm pointing, that's a right angle. So if this is theta, that means this angle here that I've drawn with purple is 90 minus theta, okay? And now in this tall right triangle that has this solid line, this dotted line is the hypotenuse, and if this is 90 minus theta, here's my right angle here, and that means theta then shows up over here. So whatever the angle of incline is will always show up between the weight vector and the y-axis, okay? That will be the same angle theta as over here. All right, so there are our force diagrams for those four scenarios. And now let's do a sample problem. This is the one on page 146. Let me turn the page here. There we go. This is what it looks like on page 146. Okay, here we go. So a student moves a box of books by attaching a rope to the box and pulling with a force of 90 newtons and an angle of 30 degrees. All right. The box of books has a mass of 20 kilograms, and the coefficient of sliding friction, also called kinetic friction, between the bottom of the box and the sidewalk is 0.5. Find the acceleration of the box. So all these problems, the first thing you want to do is draw your force diagram. Okay? So right here where my arrow is pointing, that is the center of mass of the box. They have not even bothered to draw the box. That's okay. Okay? That's the center of mass. And notice all the vectors, the tail of the vector originates at the center of mass of the box. I like to use W. Sometimes you'll see Fg for the force of gravity. That's the weight. And then the ground, since the ground is horizontal, the normal force points straight up. His applied force, which is the pulling force of the rope, is at an angle of 30 degrees to the right. And the kinetic friction opposes the motion, so it is to the left. So there are my forces acting on the box. I look at those forces, and if I choose the direction of motion to be the x-axis, That means the weight and the normal force are on the y-axis. The kinetic frictional force is on the negative x-axis, and my applied force has x and y components to it. So that's what I'm going to do first. I want to take the applied force and resolve it into its x and y components. And in the y direction, which is the up and down direction, the crate is not moving. So I know the acceleration is 0. So Newton's second law of force equals mass times acceleration. It's 0 because acceleration is 0. Okay, and also in the y direction that's how I'm going to be able to find out what the normal force is, by solving this y equation. And once I know the normal force, that's going to allow me to figure out how much friction I have, because friction is the coefficient of kinetic friction times the normal force, and then I will use that frictional force in my expression for some of the forces in the x direction. Okay, so that's the plan. So here we go. First, our applied force in the y direction is the y component of that force, excuse me. So the y component uses the side opposite of the 30 degrees. So that means I'll multiply my applied force times the sine of the angle, and I see that the y component of the applied force is 45 newtons, and using the cosine, the x component of the applied force is 77.9. Okay. My weight is the mass times 9.8, so that's 196 newtons downward. So that's my Fg. And I see in the y direction I have 3 forces, Fg, Fn, and the y component of F applied. So here it shows the sum of the forces in the y. There are 3 of them. The normal force and the y component of the applied force are upward, so they're positive, and gravity is downward, so it's negative, and they add to 0, and that allows me to solve for the normal force, 151 newtons. Now I can use that in my equation for the frictional force, mu times the normal force. They told me the coefficient of friction was 0.5, so multiplying that by the normal force gives me 75.5 newtons of friction, which is my Fk. And that's to the left. So when I sum my forces in the x direction, the x component of the applied force is positive and the kinetic frictional force is negative, and that equals mass times acceleration. In the x direction, the box is accelerating. The mass of the box is 20. There's my sum of the forces. I can solve that equation now for the acceleration of the box, and I get 0.12 meters per second squared to the right. All right. And last step, evaluate. The normal force is not equal in magnitude to the weight like it often is, but this time it is not, because there is another force in the y direction, which is that y component of the tension of the rope, of the pulling force. If you don't have other forces in the y direction, which is a common case, then the weight is equal to the normal force. But once you add any other forces in the y direction, then the normal force is no longer equal to the weight. So you got to watch out for that. Okay?